Good morning and welcome to the session 3 part 2. In the previous session we have discussed about the types of automation and types of robots in my view, in my perception, and some ingredients of smart devices or classification of these smart devices. In this session we will discuss about real-time systems, types of real-time systems, and the components of the real-time system. All right. So this is the era of complete digitization. The conventional analog systems like we used to have transistorized radios, if not vacuum tubes, or IC-based radios, IC or transistorized tape recorders, IC or transistorized televisions. This is almost obsolete now. That's what my previous session I was telling. Now, even this consumer applications, almost they're all digital now. Today we are using FM or AM, whatever, but they're digital devices, iPods, no more the tape recorders or tape-based VCRs. We are using flash pen drives for storing our audio, video files. Television broadcasting is happening through satellites directly, D2H, direct to home, through set-top boxes we are receiving. And beyond that, we discussed about the smart televisions which are connected to the data centers. So one step beyond this, we are talking about our air conditioners, refrigerators, two-wheelers, four-wheelers, charging stations, including home security, surveillance cameras, like that you name any device. Now we are talking about these devices are connected to the internet. So in the sense it is a computerization of the objects. It is not computer definitely, but computerizing these objects means there is a CPU, there is a memory, there is a program, there is input devices, output devices, but definitely not computer operating system, computer CPU, computer peripherals. Means no that LCD screen, no more ASCII keyboard, no more hard disk, no more Windows or Linux operating system, no more Intel CPUs like i3, i5, i7. They are not used. Equivalents of those things in a different form, they are available. So it is a choice of choosing your peripherals, CPU, software, hardware. It's a choice. It's a really trillion-dollar industry. Trillion-dollar industry. Majority of the country's budget is also not trillions, but however, this industry is a trillion-dollar industry. So technology is, if any country is progressed, they are progressed because of the technology, not because of agriculture or horticulture or minerals, right? Okay, so it's a choice of choosing the software and hardware. It's a combination. Any product, when you see, how do you partition the software and hardware? What is the percentage? 50-50, 70-30, 60-40, 90-10, or 100% software, 100% hardware? What is the choice? How do you measure it? What is the unit? Is it kilogram or some meters, liters? And how do you measure the volume percentage of the software and hardware? So it's a really interesting topic: software hardware partition, digitization, computerization. Let us see over a period of time and during this course we will discuss about these points again and again. Okay, so since I am saying computerization of the objects, let us first look at what is computer and the basic blocks. We all know, first, computer without operating system, there is no computer. Earlier it was DOS, disk operating system. Later on, from maybe from 1990s, we have this user interface through graphics called Windows, then Linux operating systems. Maybe now we have Mac operating system. So there is a boot process. Always operating system is loaded from the secondary storage devices. Initially it was through floppy drives. Later on it is hard disk. Now we have solid state drives, SSD. But no, booting can also happen through pen drives or LAN, whatever, servers. But there is a boot process. So whenever you switch on your computer, first it will look for the bootable files. So the operating system has some files which are located through your system CMOS setup. So whatever your system is configured, from where to look for these operating system files. Traditionally we know DOS.h or IO.h. Some no, there are some operating system files. So these files are located either in the hard disk or in the floppy disk or in the pen drive, wherever. It looks for those bootable files. So once the bootable files are loaded, then those files will load the rest of the operating system, including the device drivers. What is device driver? Device driver is a piece of code which connects to hardwares. Let's say keyboard and computer, means CPU, or monitor and CPU, like that. There are two different devices, but then some initialization programs are required to recognize, to communicate, to translate. So a piece of code is loaded. There are some default device drivers and there are some installable device drivers. So while loading the operating system, these default device drivers are also loaded into the primary memory. Your boot memory is a secondary memory, but you have a semiconductor memory in your computer, which is a primary memory. Again, there you have even primary memory is also classified as a dynamic RAM, static RAM, cache. Again in cache, L1 cache, L2 cache, and so on. So operating system is not executed from the secondary memories. Operating system has to be loaded into your read write memory, RAM, what is called primary memory, and from there it will start executing. So in short, your primary memory is partitioned in such a way that some part of the memory is allocated for loading the operating system and device drivers, And so that means it is reserved, some space is reserved. And the rest of the memory is meant for the application programs. There are some application programs which are already installed, which are registered in the operating system files. So they will be get it loaded while loading the after loading the operating system. So once the system is ready with the operating system, application programs, device drivers, then it will allow you to open the user specific application programs like compilers, C, C++, Java, Python, whatever. You can load your own application program and start writing application specific programs, what we call as a compilers. A compiler can make use of inbuilt libraries, inbuilt device drivers, inbuilt some system files, because they are part of the your motherboard CMOS or read-only memories. So it can make use of some functions, inbuilt functions, what is called service routines. So finally it will link all these files and create one binary file, what is called executable file, right? So this executable file is loaded into the memory space which is not reserved. The reserved one means the one which is for operating system, device driver, and so on. Unreserved space where the user defined real time, when you whatever you have typed will be stored into that space. So what does it mean? It means that whatever is the program you develop, it is dynamically loaded into the primary space as and when that particular space is available. So it is not reserved. It depends. It depends on how much space is occupied by the operating system, how much space is loaded, used by device drivers, then whatever the space left, there your application programs are loaded. They are dynamically relocatable files. So that's why we called as a exe files or com files in the computer, because they are not absolute memory. Absolute memory means fixed memory location. It is not possible in computer. Application programs cannot be loaded in the absolute memory, because the computer itself, as we all know, it is called virtual memory concept. Virtual memory means not real, not physical, it is virtual. And this virtuality is all part and parcel of the operating system. And it does this virtuality is because it is having a secondary storage memory beyond the primary memory. It's not real, it's virtual. So your primary memory is managed. That's why we call it as a memory management. Your primary memory is getting managed with the help of the secondary memory. Secondary memory is huge in size. Primary memory is, as compared to that, is very small. Let's say you have a secondary storage hard disk is in terabytes. But how much primary memory you have in your computer is maybe earlier it was few megabytes, right? 8 MB, 16 MB, like that. Now today we have 1 GB, 2 GB, 4 GB, 8 GB, like that. But definitely not beyond 8 GB or 16 GB. That also it's expensive. But your secondary storage in terabytes, right? 1 terabytes, 2 terabytes, 4 terabytes. Or you can also have a USB based secondary storage and so on. Okay, so this is the story of a computer desktop systems traditionally last 40 years. The process is same. The standard input outputs are same. The primary memory, the entire hierarchy of the memory is same. Nothing is changed. That's why computer is a standard system. Alright, so as compared to these personal computers, desktop systems, whatever we are talking about in this course, digitization of the objects or the applications of this robotics or automation, smart devices, other than computers. It's a very simple term. Computer versus other than computers. Wherever you see software and hardware, that is called, we call as a either embedded systems or cyber physical systems. Today we call cyber physical systems because they are also using some communication protocols like internet, Wi-Fi, Bluetooth. You don't see any hard disk other than computer. Including your mobile phone, there is no hard disk, there is no secondary storage. Everything is a semiconductor, RAM, ROM, flash, whatever. So there is no virtuality here. Everything is physical, real. So that entire boot process, even if operating system is there, operating system is part of the application program. Whenever you develop any of these applications, products, other than computer, if you require operating system, then operating system and application programs are together you have to develop. It's not that first I will develop the operating system, then operating system will be loaded, then application program. No. It is a single file, single binary file. Since there is no secondary storage, there is nothing like relocatable programs. I know at this stage it is slightly difficult to understand, but since I am recording my talk later at later stage, again you can refer that what I am talking when you start writing the programs. So there is no relocatability here. Whatever is the program we are writing into the memory, everything is absolute memory, physical, real memory. So even if you have an operating system and the application program, the memory space where to load is predefined. You can classify your memory. Where is the storage space? Where is my variables? Where is my main memory? Where is my data types? Where is my buffer? Whatever you want to classify. But it is absolute address, no relocatability here. Alright, so keeping in mind these aspects, development of a software and hardware other than computer, we call it as a real-time systems or embedded systems or cyber physical systems. They doesn't use Intel architecture, Microsoft operating system, IBM system design. It's not that. They're limited only for desktop systems. That's all. So this is all custom designed systems. That's why we have designed our product like that. No, all applications they design. Air conditioner has a different design. refrigerator has a different design, mobile has a different design, two-wheelers has a different design. Every product has a different design. Every device has a CPU, every device has a software, but the design is not same. So the heart of any system is the CPU, and if you want that system as a smart device, then naturally it requires some operating system. You need to develop a real-time operating system called kernel. You cannot write a simple program like on-off type. The algorithm has to be, there should be some components which will take care of linearity, stability, accuracy, and so on. So the algorithms are not so simple. Like when you are traveling by two-wheeler, right? Engine is IC engine, but how do you feel when you are traveling by four-wheeler? Engine is same petrol, same IC engine, but how do you feel? If you are traveling by slightly expensive four-wheeler, how do you feel the comfortness? If you are traveling by a luxurious car, though it is using four wheels, rubber, plastic, metal, petrol, IC engine, but the comfortness is different. If you are traveling by a low-cost aeroplane, how do you feel while take off, take on? But at the same time, if you are traveling by some expensive Boeing or some other flights, how do you feel is different. What is that difference is all about control system. The heart of any system, it is not the metal, it's not the rubber, it's not the steel, it's not the fuel, it is something else, right? Money people are paying for that. Okay, so since it is a computational device, and if your algorithm is complicated, then you require a slightly better computational device. So how do you represent? Finally, it is boiled down to the numbers, numbering system. How do you represent the number? 4-bit, 8-bit, 16-bit, 32-bit, 64-bit. Let's say, for example, you are measuring the temperature. So when you display the temperature, any instrument, how many digits you are using to display the temperature? Or when you are using a calculator, when you are calculating some numbers, how many digits you are using? When you are purchasing some food grains in the shop, whatever is the weighing machine is showing, how many digits it is using. If you go to a gold shop and if you are buying the gold and if he is measuring by using weighing machine, is the weighing machine is same as what you are using in the grocery shop, or it's a different? Understood? So it matters when you are representing a number, and if the number of bits are less, that means you are neglecting some information. You are rounding the numbers, the fractional part or even the BCD numbers. If you are limited to the numbers, that means you have omitted the rest of the portion of your, either it's a multiplication or division or accumulation, whatever. You didn't consider that because you have limited your number. So day by day, as you might have noticed, this size of the numbers representation is increasing because the CPU are having more bits to represent the numbers, right? The data, what we call as the data size. So if you expect this such a complicated algorithms to be executed, then you also look for the CPUs which are having larger word size. So that's the one of the criteria while choosing the CPUs, because you are worried about the real timeness, accuracy, as well as the smartness. Similarly, which programming language you want to use. When it comes to computer, you all know there's a wide varieties of languages. C, C++, Java, VB, .NET, Python, and so on. So many languages are emerging. 1990s, people are using assembly language. Even for computers, right, we have used assembly languages in 1980s. Assembly language is not user friendly. It is user friendly to the CPU, but not to the user, not to the humans. But it will give you the best possible performance, optimized code. But since it is not user friendly to human beings, from 90s onwards, they are not using assembly language programs. So C is widely used even in other than computers. Even today also 80% of the applications in embedded systems, that is cyber physical systems, we are using C language. So now also we call it as a C. Maybe the end of this session we will try to compare how it is different from the C language which you are using in the computer. What way it is different. Otherwise the C++, Java and all, we don't use these languages other than computer because they occupy a lot of space. And as I told you, since we do not have hard disk secondary storage devices, we try to avoid such kind of compilers. So mostly, almost the entire industry is using C as a compiler for other than computers, but it is called embedded C. Okay, now let us compare or let us look at the CPUs. The CPU which we use in computer is called microprocessor. Microprocessors are used only in computers, nowhere else. It is as good as obsolete technology, like i3, i5, i7. They are used only in computer. They are not used not even a mobile. They don't use these CPUs. So what CPU we use other than computer is called microcontroller. What way it is different from microprocessor? A microprocessor, as the name says, the heart of the microprocessor is computational unit. But what about the memory? Memory is not there inside the microprocessor. What about the peripherals? Peripherals means like inputs, outputs, timers, analog to digital, digital to analog, multimedia. All those things are not part of the CPU. But when it comes to microcontroller, it's not only computational device. The core is not only CPU, but it also integrated with your RAM, ROM, inputs, outputs, timers, ADC, everything, clock, everything. That's why they are called single chip device. For example, you open your calculator, you will find microcontroller. You open your mobile phone, like you name any product other than computer, all of them are single chip devices. But then why not in computer? Why microcontroller is not there in computer? As I told you, it is obsolete technology, right? For several 30, 40 years we have used microprocessors. But then computer is getting obsolete. Now we are not using microprocessors no more other than computer. So you will get the best possible performance if everything is integrated in one single chip. That's why microcontrollers are popular. And it will be save your space, cost, and it will reduce the power consumption and performance it is giving. So in all respects, microcontrollers are preferable. So in this EDU-ROBO training program also, undoubtedly, we are going to use microcontrollers. But then I was telling about real-time software development, means operating system, application programs. How will you make them real-time? So now the question arises here is, what do you mean by real-time? What is real-time? What is real-time? Real-time is not about the speed. We have a misconcept that real time means how fast. Absolutely no, it is not about the speed. Real time means in time, natural time. If you have any system which is following the natural time, that is called real time. Let's say, for example, you have a air conditioner which is maintaining the room temperature in time, then it's called real time system. You have a lift, you are traveling by lift, and the lift is following the time, right? Whenever it is crossing the floor, whenever it is reaching the floor, whenever it is closing the doors, if it is following the time, natural time, it is real time. When you are traveling by a metro train, locomotive, and whenever it is reaching the station, how the brakes are applied, whenever it is leaving the station, how the motor is accelerating, and the rest of the control things are following the natural time, it is called real time. What do you mean by non-real time? Non-real time means, let's say for example, you are watching a movie and the audio video is not following the time. You might have noticed sometimes audio will come first or video will come first and so on, right? I mean, there's a mismatch. They are not following the natural time. So we are not interested before or after. We are interested in time, in time. For example, exactly at 12 o'clock, this satellite should be launched. Not before 12, not after 12. At 12, that is called real time. Calendar. At 10 microseconds, I want this thing to be measured. That means exactly at 10 microseconds, that should be measured, that should be generated, and so on. So in time, computer unfortunately is but it's not real time. Why it is so? Because the operating system has its own priorities. Which program to run when? You might have noticed even the virus also started getting loaded, and the virus is given the highest priority. Your programs are running at the lowest priority. You have seen. You also have seen that every day your computer's execution speed is changing. Sometimes fast, eventually it is becoming slow. When you have formatted the entire operating system, application programs, the performance is much better. Eventually it is getting slow. This you might have noticed in mobile phones also. So why it is so? The timeliness, it is not following. So whenever they are not following the natural time, they are called non-real time systems. So our products, right, whatever we are talking other than computer, we wish they're all real time, because we are not using Microsoft or Linux operating system. Whatever is the operating system we are going to write, whatever is the application program we are going to develop, it is real time. It should follow, for example, every day at 1 o'clock, right? This particular device should be on, fan should be on, bulb should be on, gate should be open. That means 365 days, 24 by 7, as soon as that particular time is reached, that event should happen. It is nothing to do with the day or month or year. Irrespective of that, this entire life of that particular device, it should follow the time. Please remember this. It's a very, very important concept. Very rarely people understood about real time. So how to make your system real time? So please remember this slide. It's a little bit complicated. It's too early to discuss about it. But since I want to tell you about what you mean by real time, as I said, the structure, the software, mainly software development is altogether is different. Please remember, real time is nothing to do with the hardware. Of course, there is a small dependency is there, but as I was telling you, in spite of having a 3 to 4 gigahertz of computer, you are unable to follow the time. At the same time, the refrigerator is using 40 years old CPU. Still, it is following the time. That's the difference. Okay, so we will discuss this maybe in future when we talk about more on structured programming, real-time programming. Then we will discuss again on this slide about what is real-time software development. So while choosing the controllers, it is a choice. Again, let's not worry about this slide. But CPU selection is really a choice. In the market, you will find thousands of CPUs, many, many companies. More than 30, 35 popular companies are there in the market for selection of the CPU. However, in computer, you do not have much choice. Only one brand or 2, 3 models. But in our case, yes, since we are not talking about computer, we have a wide variety of choice. So we will discuss this slide once again when we talk about more on application designs. I was telling about real time. Maybe in a graphically, if I want to explain, let's say, for example, if t is equal to 0, you have the sample called n, and exactly at n plus 1, right, you want this entire thing to be completed. Not before, not after. Let's say, for example, t is equal to 0. Then after 10 microseconds, that's what I'm saying, delta t. That means n plus delta t. That means n plus 1. I want that to be completed. Let's say you have not completed, right? By t plus delta t, you have not completed. What will happen? Let's say you have a missile guided system, and then it has detected one missile is going to hit the radar. So what is real time? At t plus the delta t, right? Maybe whatever the your calculated this thing, it should hit the missile. Not before, right? Not after. Then it is meaningless. It should be in time. When you want to catch a flight, right? I hope you can understand what is the significance of in time. What will happen if you reach before? What will happen if you reach after? It has a different kind of repercussions. But then in time, if you are not there, you may miss the flight, or you have to spend some time, waste your time at the airports. So keep it in mind. In time means natural time, and natural time means not before or not after, in time. If I look at my spectrum of applications, like I told you about computer, then you all know games, internet, or today we are talking about cruise control, telecommunication, flight control, engine control, and so on. So you can classify them, that are they really real time, or it's okay sometimes real time, sometimes offline, non-real time, or 100% real time. There is no question of missing that, like nuclear power reactor. Absolutely, there is no question of missing that event. If it misses, or like no satellites or bullet trains or flights, rockets, missiles, when you miss it, you know it is a catastrophic. There's no question of missing that. For example, you have a four-wheeler and there is a engine control, automatic brakes control, and if it misses, then what will happen? So they are called hard real time. Soft real time means, let's say you are watching a TV through set-top box, and sometimes due to some communication problem, one or two frames are missed. What will happen, right? Nobody will die, or the picture quality won't be deteriorated. Slight jerk, some glitch may happens, and that's all. Even sometimes you don't even notice also. Non-real time, already said about computer. Even if you draw something, if you display something, sometimes it's fast, sometimes it's slow, sometimes in time. So we cannot predict the computational thing of the computer. So it's non-real time. So generally computer simulations are non-real time. So look at your application. What is that you are automizing, making smart? Accordingly, the software development, isn't it? The kind of structure you create while writing the software development is altogether different. That's why this entire course I named as a real-time software development. Computer also, it is supposed to be real time, but since operating system is not developed by us, there is a possibility of non-real time there. But other than computer, wherever, whatever you see, software, hardware development is developed by us, including operating system. So if you want, you can make them real time, soft real time. It's in your hand. Nobody can stop you making them real time, because we are not depend on these companies. Absolutely no assumptions. In computer, you make lot of assumptions because you have not written the operating system. You have not developed the hardware. So you have to make the assumptions. It is like that only. Then you develop the software. Okay, so I already said real time is not about the speed. It is only in time, on time. But then based on the time guaranteeness, they are classified soft real time, hard real time. So soft real time is like your iPods, satellite TV reception and all. Even if it miss very rarely, nothing will happen, no catastrophic, a small glitch may happen. Hard real time means as good as like a healthcare sector. If something happens, patient is dead. If something happens, maybe right entire state, country, anything can happen, right? So there is no question of missing that event. They are called hard real-time systems. So if you can afford to miss the events, then go for soft real-time. Not necessary that every system should be hard real-time. because it's complicated, reliable to develop the hard real times. So it's okay, sometimes you can be a soft real time. So naturally, if you want to develop the real time software, the programming skills are different. That's why I'm saying this course is why it is important, because it's not about computer programming development. It is other than billions of applications. The entire future is about software and hardware development other than computers. Today, who is using computer? Nobody is using computer. Entire this financial, this banking is happening other than computers. People are using mobiles. People are using televisions, set-top boxes, or look at your own four-wheeler is doing the banking transaction, right? It is connecting to your account. It is deducting the money. Like that, all these devices are connected to your financial sector. Such a sensitive area, right? Or other than computers. So that's why I'm saying why it is important is because no more this computer operating system and computer compilers. We don't develop computers, right? We are only using the computers. But when it comes to other than computers, we develop the hardware. So that's why I'm saying you should equally know how to design and develop the hardware. Otherwise, it's like, general. You are one of the millions of people where you understand only programming in computer. But then everybody knows about the computer. From school education itself, people know how to use computer and compilers. So what is there? Nobody teaches the computer architecture. Nobody teaches the computer peripherals, programming, device drivers. Nobody writes the operating system for computer. So everybody knows about computer and computer software development. But if you want to be unique, if you expect some, right, the better development jobs or career plans, ideas, product development, then yes, I mean, no assumptions absolutely. You should know the software and hardware development partition, real-timeness. Okay, so please remember in this entire journey, though we use the computer, please remember we use computer of course to write the programs. But then after writing the program won't be there in the computer. The computer is actually, we are transferring the program. Please remember this slide we repeat again and again. This entire training program. The program we are typing using computer like Arduino as a compiler. We will discuss why Arduino. But the program is transferred from computer to our this green and this orange, right? Or you can say pink is what is our hardware, this entire thing. So we transfer the program from the computer to the system. We named as a EDU-ROBO, whatever, but it's a Atmega, you can see some 328 CPU and connected to USB by using some converter, and we are programming. So this is called real-time emulation. What is real-time here? Because my program is not running on the computer. I only typed on the computer, but finally it is executing on my CPU. Target device is different. So naturally, since no Microsoft, no Linux here, it is executing in a natural time, real time. That is one of the biggest constraint we have in computer, because here you have a Linux or Windows. That we have done because this entire thing is designed as per the application and no more computer sort of a assumptions. And it is emulation because real hardware is there. It is not simulation. People does simulation by using computer. We are not doing simulation. We are emulating the entire thing on a real platform. And whenever you modify it, again you compile it, again you transfer it, again you emulate it. So almost 90% of your code, whatever you are developing, is as close as possible to your application. But if you do simulation, once again you are making a lot of assumptions. The real hardware, how it will perform, how it will react to the real constraints, any delays, all these things are, you have made a lot of assumptions, not real peripherals, and so on. So there is a possibility of mismatch. Okay, so we prefer that. We don't prefer simulation because finally it is a product development, software, hardware development. So let us develop our own hardware and let us program in our own system. Okay, so programming is same as the way we write in computer. We use some editor and we type our program like a C extension .c or something like that. And after compiling, it will create the binary files, and it also make use of some libraries, no problem. But what I was telling you earlier is that the output file is an absolute address, not like computers relocatable. No, it is absolute. So that's why this is called hexa file, Intel hex file, which is absolute memory mapping, no relocatability, isn't it? So this is how our programming structure, more or less same as computer, but last at the end there is a difference. This is absolute addressing because we are not dynamically relocating from secondary memory to primary memory. Within the primary memory also, every day my address is changing based on the situation. No, that doesn't happen other than computer because there is no Microsoft or Linux operating system here. Okay, so before I conclude, let us compare the C compiler of computer versus the C compiler of this embedded systems or cyber physical systems. Actually, syntax is same. If you know at least the syntax of C, then that means you don't need to learn any new language. You don't need to know even full C compiler. You don't need to know all the functions of C because no, embedded C is very tiny model. Maybe in 1 or 2 days also you can learn about the syntax of C as far as embedded C is concerned. But then there is a difference. What is the difference? The difference is here, in computer we don't initialize the hardware. Let's say, for example, you are using some timers, you are using keyboard, you are using display, like that you are using some peripherals. You don't write any hardware related programs when you write any application program. For example, you say printf. What do you mean by printf? You want to display something on your computer screen. That is the C. In C you write printf. But then have you initialized the computer monitor? You haven't done. Similarly, you say scanf. Have you initialized the computer keyboard? You haven't done. But then you say simply scanf printf. Without initializing the computer screen, computer keyboard, it won't work. In reality, it won't work. But how this is happening is because it is already taken care by some inbuilt functions, which is done by your, some of them are done by your BIOS, where you have some programs on your computer, inbuilt in the computer itself, on your motherboard memory. And operating system also does some initialization by loading the operating system itself. That I told you about the device drivers. Some of them are installed, some of them are default. However, in our case, when I am not using computer operating system, so are no inbuilt motherboard sort of a architecture or memory programs, then every single peripheral input, output, keyboard, anything you use, you are supposed to initialize. So that is the biggest difference between embedded C and a normal C. In normal C, generally we don't bother about hardware initialization, such type of functions. But in embedded C, we are supposed to do that. Similarly, about the CPU. In normal C, we always assume that the CPU is Intel. Always Intel. Architecture is Intel. Last 40 years, computer means Intel. But when I am saying including mobile phones, we don't use Intel CPUs. Nowhere. It is a choice, wide variety of choice. Several companies, several CPUs. So when you write a program, your embedded C belongs to which company? It is not same. Company to company embedded C compiler is different. Target CPU is different. Peripherals are different. So slightly the functions won't be same. They are different. So don't make any assumptions that printf, scanf as it is will work in embedded C. No, they don't work, because every company has their own way of dealing with the peripherals. Last 40 years, computer means, printf means that standard monitor, and the text is also, there is a resolution 80 by 25, something like that. Keyboard means always ASCII keyboard. But now tell me, which system has ASCII keyboard and computer monitor? Does your AC has? Does your refrigerator has? Does your washing? Nowhere. You may be having LEDs, LCDs, 7-segment displays, touch screens, sensors, and so on. So printf, scanf is, the definition is not same when it comes to embedded C. So please remember, since the user has a wide variety of choice of input and output devices, so your standard stdio.h, standard input outputs, what you use in Turbo C or in computer compiler is not same in embedded C, because here I have a choice. So don't think that libraries which are provided in embedded C as it is will work for every application. No, because this area itself is a custom designed system. We design the system hardware as per the application. So as it is, the functions doesn't work. That is the beauty. We always create our own functions. Our standard input outputs are changing. So it is a choice. So finally, embedded C is a choice. Hardware target device is a choice. Peripherals is a choice. So compiler is altogether is a different for different companies, different architectures. Though syntax is same C syntax, you don't need to learn a new syntax. The way you define the variables, the way you define the functions, the way you define the structure, the way you use the conditional statements, everything is same. However, embedded C is very, very small. It is not a floating point. First of all, CPUs are not floating point. It is very, very rare using a floating point CPUs in other than computer is very rare. Even mobiles are not having floating point CPUs. Majority of them, 90% of the mobiles doesn't use floating point. So it is a downscaled version. Most of the CPUs in these cyber physical systems are 8-bit, not even 16-bit. However, every computer today is 64-bit and they are going by 128-bit. multi-core. But in our case, only one CPU, not multiple cores. No multiple CPU concept here, single core. Okay, so I don't need to teach a C language because C language is same. But what I am going to teach in these three levels, I mean, why am I teaching three levels? Why do you require 6 months? At least you should practice, is because I am going to teach you hardware initialization. That means generally these things are not part of your schools or colleges. Every day the peripherals are changing, the CPUs are changing. So we need to understand, tomorrow if you buy a new sensor or new communication device, it has a different kind of programming which doesn't come with the compiler. So we are supposed to either write, or if it is available, we should know how to make a patch. That we will see as a part of this course, starting from simple numbering system, simple numbers, your 7th standard numbers, if you know, how to represent those numbers in the program, how to use your mathematical functions, right? Whatever you have studied in trigonometry or whatever, differential equations, integrations, how to represent those mathematics in the program, in embedded C program. Also the subjects like physics, right? You may be having some formulas, how to write those formulas